All right. Well, today we are so happy to have one of our own professors here to give us a really interesting topic. But before we going any further, I wanted to have a brief introduction about Dr. Shaw. And I actually never shared this with him on this topic before, but Dr. Shaw is really one of these pioneers and actually a role model for me. So when I was at grad school, I stumbled upon a book that was first authored by him. I think it was published in 1995. And I was so amazed that both of us are from original from China, with a book that is from front to the back, all in English. That gave me some kind of sort of a hope to look for, in a sense. It was like, can we do that? Right? And so really that's an inspiration. I never shared this with him. It's a book that back then is too expensive for me to buy. I copied a couple of chapters. I read it as a grad student. And then I met with him 10 years later at one of the SF conference in 2006 or 2007. I met with him in person. And I was so happy to introduce myself to him. I said, I read your book, and you were one, and then he showed me something else. He showed me one of his tool that he made called the M5 tool, so the program that he did. And that was a further inspiration. I was like, wow, we can do that. I was a new assistant professor. And so really, he has been inspirational to me. And today, even, he one of the topics I think a lot of people have struggled with, and he's coming up with something brand new. So I'll be really curious to hear what he's going to say about this. So welcome.
Thank you, Song, for your nice introduction. There's a Chinese saying that 好汉不提当年勇 means never talk about the past. Past is past. Right? Now Song is hero, right? We all know that. All right, just as Song said, I spent a few years examining the accuracy issues in remote sensing. And so during the pandemic season, so locked in room, nowhere to go. So I had more thought, I figured out something out. So I'm going to share this progress with you today. Let me see, which is, next slide. Next slide.
I think this one for your slide.
Yeah, no response here. Next slide. Some technical issue here. Again, this is a reminder for us. When we develop a digital forestry program, we don't want to do something like this. Make it easy. One click works. Now we have two computers, audio, share, projector.
Is this
And we have Zoom.
is this your next slide, key points?
Yeah. Okay. Is it working?
I just hit enter.
Okay, enter. Okay, now everything changed to enter. This is not us. This is construction. Okay. So I'm going to share a few points here. I will do it quickly. We lost like 15 minutes or so. So you can see that. I don't have to read it.
Let me get that out.
Okay. So errors involved in remote sensing everywhere, from the data acquisition to application. This is a nice summary from the paper as said here. So many years ago. people realize that the error is a problem. Even here today, I'm going to explain this part from the classification and to the reporting standard. Even the error assessment has errors. So we are trying to assess errors, but that part has errors. So I'm going to focus on this part. Accuracy is a very hot topic in remote sensing. If you search remote sensing literature, number 6 is this paper by Professor Conjuting. He gave us a talk last semester, last year. This published in 1991, so has been cited 4,000 plus times. This is number 6. This is unbelievable. People, every time you do classification, you want to assess accuracy. So how do you do that? This is one of the earliest paper people refer to most often. Now then, how high is high for accuracy? People talk about in remote sensing culture. This is one pioneer paper by Anderson and others, or USGS 1976. After the first Landsat satellite launch, they prepared this documentation, give people some idea, what kind of accuracy you are going to have. At that time, people had no idea how to assess accuracy, but we have general idea, similar concept. The accuracy will probably be 80% minimum. That's the kind of criteria. People still refer to this. If you want to publish a remote sensing paper, you report accuracy. If accuracy is about 80%, 85%, normally reviewers, editors won't question it to you. This is fine. This is good. But this is a culture in remote sensing. If you look at the existing Mac product, this is a summary from another paper, not my paper, other people's paper. You can see that only one overall accuracy is about 85%, or below 85%. It's hard. To get 85% overall accuracy is not so easy. That's the point. Okay. Now, one of the most recent product, this one, is the 2019 NLCD data. I'm so happy to see this. They reached accuracy 91%, much higher than 85%. So this is a tremendous progress. When people assess accuracy, they use error matrix or confusion matrix. This is one of the examples. Binary classification. Have this in remote sensing, have actual population or reference, have classification. Actually, in other fields like computer vision, they switch the column, the root total column for the solution. So that's the culture thing too. Remote sensing is always put this reference for the column and classification for the root. But for the computer vision, other field, we just transform 90 degree. So this is something a little bit careful. When we set this thing here, we want to be careful. In computer vision, we use the recall sensitivity, specificity, and then classify the positive rate, negative rate. In remote sensing, we call it user's accuracy, producer's accuracy, different terms. The reason for remote sensing here, remote sensing always, most often, very often involves more than 2 classes. When you have more than 2 classes, this term not enough. So we have to expand it. That's another reason.
Is it better to go down below, or I just can't get this off?
Yeah. That's okay. Not big. Maybe put it on the top. That's fine.
Okay.
Yeah, that's okay. So that's the culture thing. Okay. Now use a big mixture. Many people doing remote sensing work. The computer vision people, the data analysis, engineering. Very big. If you look at the remote sensing literature, a lot of terms now available here in remote sensing terms, not just user accuracy, producer accuracy. I'm not saying this is a good term, okay? People don't like this term either. I don't like this term. But, now it's very big mix, very confusing, actually. So numerical, if you do the test, positive test, negative test, they use sensitivity and specificity, it's different. They use, so different fields have different culture. Oops, no, this is not working anymore. I say I'm sorry. This is the enter key not working anymore.
Maybe I hit the alt key and it stopped. Uh-oh. Stop and then I'm going to start share again.
Okay.
But now it's not.
Maybe you can use this. No.
No, it should be on this one. Is that it?
Now it's working.
Okay.
Use this.
Yeah.
This one. No, now I use mouse. Okay. Again, okay. We don't want to develop digital force technology with this, something like this. Now this is one simple prediction. This is the reference target. You have two maps. One is map 1, map 2. Map 1 you have it looks like a target, but bigger. Map 2 has nothing. Now you can look at the overall accuracy. And the top one, the overall accuracy on the left is 74, and in the middle is 82. So this one even has a higher accuracy than the left. The left, at least, this you see something, right? Something familiar. Something in the middle is nothing. So nothing, but overall accuracy actually is higher. So that's the okay, here, yeah, that's the issue. So overall accuracy has problems. Now, if I expand this area bigger, even bigger, everything bigger, what happens is the accuracy is even bigger. So now from 70 something to 87, and in the middle, you cannot see that, right? Middle is 91%. So everything is bigger. If you expand the area, this is two example here. Like if you make a land use land cover map for this Tiburon County area, Greater Lafayette. If you only do the urban area, you have one accuracy. If you expand to entire county, your accuracy will be better. So because agricultural land homogeneous, and you can easily increase accuracy. So that's the problem, overall accuracy. And you can change the boundary, and then you can make a false map. You do nothing, then you get a really high accuracy. So now the issue is the problem is then, and overall accuracy doesn't necessarily reflect the discriminative power of a classifier. The questions are, what does, right? Which one we can use? And people will say, okay, let's use kappa. Kappa is useful. Some people use kappa. And also a lot of people say, no, you don't want to use overall accuracy. You're using the class level accuracy methods. That's the common argument. So still the culture in remote sensing, this is a literature search, vast majority only report overall accuracy. They rarely report and class level accuracy. That's still the situation. And particularly the big project, important, significant project, they only report overall accuracy. because important people don't have time to read the confusion table. They only see one number. Oh, what's the accuracy? Okay, 85%. Oh, that's good enough. Now, that's I call this overselling. Overselling accuracy. Overselling accuracy may misinform about research reliability. Here I have at least 4 reasons. First reason is overall accuracy cannot explicitly explain the errors or uncertainties of map derivatives. So the map we derive is not the purpose. It's not the final purpose. We develop maps, but the map itself is not the purpose. We want to use the maps. For example, in our field, Soliana, we do landscape ecology. We do derive the connectivity index, fragmentation index, that kind of more dozens, maybe hundreds indices available. It cannot control. And you get 80, 90% accuracy, you cannot control at all, or whatever you're going to derive. Then the values of overall accuracy are not comparable if you have maps with different number of categories. So you have 2-category map, 4-category map, 10-category map. They are just not comparable. Then it's not so comparable. Also, you have a map of the different proportions, the classification distribution, some normal, some even distribution, some uneven. So that's the issue. Then you have a high accuracy. Doesn't mean your map is real. That's the most important issue. There's some this issue has been found, not new. This issue is not new. This has been found in many areas, like computer vision, like medical imaging. We found this issue. They rarely report over accuracy. Remote sensing still report this more. Other fields we didn't use it much, but deep learning still use this. I think a lot of deep learning models, the loss function, they still use over accuracy. Then let's look at kappa. If kappa works, this is the original paper from the author, the Cohen. He published a kappa paper. This is the equation to calculate kappa. So the one thing is no criterion for the correctness of judges. You have 2 judges, 2 evaluators, 2 people, and they have to be independent, and no one can be assumed correct. This is the assumption. All right. Then they have this equation, and then remove the chance. Chance agreement is removed. So this part is chance agreement. This part is removed. Then you have like a more reliable comparison between 2 judges. That's the thing. The key here is this one. No correctness. But in remote sensing, we collect the reference data. We know reference data is not really true, not real. But at least we assume reference data is correct. That's at least our assumption. But here in this original the paper, no such assumption can be applied. So this whole thing is the chance agreement here doesn't exist in remote sensing data. So if chance agreement doesn't exist, then this kappa cannot be used in remote sensing. That's the key issue. 2 papers, very significant papers, has been published last 10 years. If you look at the paper title, the death to kappa cannot be worse than that, right? So people read these papers, particularly the first paper published more than 2 years. This is a long paper, explain that. I think people still not really understand why this is a problem. The reason for that, I mean, this is still, they explain the kappa, they realize kappa, something wrong with kappa, but didn't really make it very clear what's wrong. People didn't understand it. So I talked to Remote Sensing Journal editor-in-chief, very reputable remote sensing scientist. He said, I don't know why kappa cannot be used. So that's the top scientist in remote sensing still don't know why kappa cannot be used. So that's why people still use kappa. You see, ordinary, if you search remote sensing keyword, you see the publication number, information. If you're using deep learning, machine learning, AI, the number, absolute number is not high, but you see the trend so steep. People using this a lot. Kappa still being used. Even kappa supposed to be dead, but still there. And one reason is no other option. We know overall accuracy has a problem. Now kappa has a problem. People said this to kappa, but people don't really understand why kappa is wrong. So people are using kappa still. Then we come to the individual class. If the individual class is okay, here, this is a paper in 1999. This is a very serious accuracy assessment paper about this global high-resolution land use land cover data accuracy assessment. After assessment, the authors found, wow, interesting. Bigger class supposed to have a higher accuracy. Smaller class has a lower accuracy. That's kind of interesting finding. Turn out, this is true in theory. It must be true. If you look at the two classes, class 1 is bigger, class 2 is a smaller, one major, one minor. Oh. Yeah, let's do it again. Okay. So class 1 is a major class, class 2 is a minor class. And if you have an equal error in the middle, you are going to have now the return key works. The class 1 accuracy must be greater than class 2. So that's if you're using binary classification, using this kind of ideal situation, that's for sure. So if you understand that, then this is no surprise. It happens often. So that means your individual class accuracy is not that dependable either. Bigger class tends to have higher accuracy. Smaller class has a smaller accuracy. This is another issue for deep learning. People, deep learning community, they complain. The deep learning models, it's hard to handle small classes. I think maybe not. Maybe the accuracy reporting problem, because a small class tend to have low accuracy. Then they thought maybe this model is not that powerful. Maybe it's not the case. I'm not a deep learning expert. That's my guess. That's possible. If you, then some other class level accuracies, including this F-score, LU, thing here. If class 1 is a major class, class 2 is a minor class, and the two classification errors are the same, identical. In this case, N12 and 21 are the same. Then the individual class accuracy, class 1 is higher than class 2. And F1 score, same thing. And LU also. So you can easily derive this thing. If this is the case, okay, have this. So this is, used very often in computer vision. LU very often in deep learning for object-based classification. They all suffer this problem. So we call this called the class imbalance effect. So it happens overall accuracy and kappa theoretically wrong, then individual class is not that useful either. or the class level accuracy as also suffers from this class imbalance effect. Then again, I mentioned earlier in the instruction. So 2 years ago, we couldn't go to anywhere. We saw the vaccine issue here, vaccine the efficacy. Then we thought maybe let's try something efficacy about classification accuracy. So that's the idea we came out. Then we use the efficacy equation. Efficacy involves vaccine, unvaccinated, two groups people, then to compare to get efficacy. Using the same concept, we derived the map level, image classification accuracy called MAS. MAS, not a perfect term, but something maybe easy to remember. And here on the top there, I think this is wow, you are good. You are good. All right. So the control here, the baseline classification is random classification. Then we came out this equation. This equation looks so like kappa, very close. Only difference is kappa use both the classification photo and the reference photo. Now this one only use the reference photo. So the target classification accuracy A is independent from the baseline classification. The two groups are different, independent. For kappa, it's not really independent because the second part of the baseline also involves classification photo. So classification is part of that baseline number. So that's not independent. And also we can get the okay. No, it's mouse. So when under perfect situation, the max value is 1. If this is classification equals the baseline classification, then it's 0. If below 0, that means this classification is worse than random classification. So random classification is a baseline classification in this case. Then you can use this equation to calculate the class level efficacies. Here, I will show you a few examples to explain the effectiveness. Here, I compare 4 data sets: global land cover, global burn area data, US NLCD level 1, US NLCD level 2. Blue is overall accuracy. And then global burn area overall accuracy is almost 100%. You know, the global burning area is really small proportion in entire land surface, right? Only a small proportion, 1%, 2%, very small proportion. Even in California keeps burning, but that's a small place. Or if you look at the global level. Then if you compare this effective max value, this max has the lowest quality. If overall accuracy shows high quality, but efficacy shows the lowest quality. The reason for that is the unevenness of distribution contribute too much to overall accuracy. But after that part corrected, the efficacy value is much lower. So now you can tell other 3 data sets are fine, are okay. Only this one, the burn area or at the global level. So it's changed a lot. I mean, this is a 100% accuracy is very misleading. You know that, right? It's very misleading. But they report it this way. Here is my class experiment from last semester. I had 15 students in the class. We did a classification experiment for Philippine content area. 4 classes, urban, 4 agricultural regions. And the standard deviation here, that's because every student has different map. That's natural. So we have 15 maps. We've got the mean value, the standard deviation. The blue again is overall accuracy, and on the picture as chart, the bar chart on the left is accuracy, and on the right is efficacy. If you only using the accuracy to compare the classification, agricultural water has highest accuracy. If you look at new users, user accuracy and producer accuracy. But when efficacy is used, agricultural land accuracy is low. And now these two become close. Forest agriculture is close. Water is still high. Water in this area easy to classify. And so easy to classify, so homogeneous, easy. But agriculture is a dominant landscape, account for 64% in chemical content. So when you reduce the area distribution effect, its efficacy level now becomes similar to forest. So that's the shows the effectiveness, or at least the difference between accuracy and efficacy. Then here we use the deep learning models. I borrowed Sony's graduate student. They helped me run a few models, 4 models, same data. This is urban building detection data set. This data set, 15% building, 85% non-building. So 2 classes, uneven distribution. So you can see that this model is the best, right? This the model 4 is the best. So that's easy to tell. But we don't know how bad the first 3 models are, how bad they are. And you look at the traditional class level accuracy here, here class 1, class 2 is always greater than class 2, except for this one. In general, class 2 is better because class 2 has a bigger share, larger share. Now, then look at the accuracy. The class 2 accuracy actually becomes negative. Negative means worse than random classification. If you're using the traditional accuracy evaluation measures, class 2 is supposed to be better. Turns out, class 2 is a problem. Class 2 is negative in this case. So, everybody will choose number 4, model 4, because even you don't use it, you can still choose number 4. That's not a problem. That's okay. Only issue is, what is the problem? What is the classification problem? It happens to the minor class or major class. If you look at this map, this thing here is minor class has problems because accuracy is low. That's low because the proportion. Then we use a model number 4. Use same model, same data. Then to get for the testing purpose, using different proportions. 10 to 90, 15, 85, 32 to 68. Look at the over accuracy and decrease a little bit, right? From 0.9 to 0.85, actually decrease a lot. But the efficacy almost equal. It's very stable. This makes sense. This is the same model, one single model. Same model, just when you do the testing, just the proportion is different, change. Something comes up like this. So that means the efficacy is effective to evaluate model's performance. So this is example is some kind of this convincing example. Again, let's come back to the target map. Okay. I have two maps, all right. One is 74%, one is 87%. Okay. Then if you look at this is the proportion. This map proportion is 0.8, 80%, 17%, 90%, 10%. That's the rough proportion. So this has a high uneven distribution. Again, the same thing. The class major is red, and minor is white. So minor class has a low accuracy. Okay, the producer accuracy and the user's accuracy, but is the major class has problems. The major class is negative for efficacy. The same thing to this. So this is major class. Its efficacy is negative. But if you look at the conventional accuracy numbers, the minor class has problems. Now, we saw over accuracy is a problem, but there's something even worse here. This is one extreme example. One of the students did tree counting using US data for Martel Forest. She did, after that, she said, wow, the tree counting is so close, like 95%, 98, 90, I don't remember exactly, 95 at least, agreement between the number of trees and the counted the reference and the trees counted using US data. I said, maybe that's not the right way to validate this classification. So this is one example I'll show you. The reference data has 10 trees. The classification also has 10 trees. And 10, 100%, right? 100%. You have 10 trees on ground. Your map, your classification result, you got 10 trees, 100%. If you only look at that, right? This is worse than over accuracy. But this is missing. 2 trees are missing. And then this is not tree classified as tree. This is one single tree turned out classified as 2 trees. This is the problem. Then how can you assess it? So now you can, using your reference, based on the reference, you can get one error mission table. If you based on your classification, you can get another error mission table. So what happens is you only have recall precision, and no other. Okay, you only have the tree class, users actually, producers actually, and users actually. And the user actually, users actually. The thing is, if you based on the reference data, the precision always 1. If you use the classification as the to start with to collect the data to assess it, then your recall is always 1. So what should we do? And so my guess here in this case, didn't study this. Maybe you do 50% this way, 50% this way. And now you can look at accuracy. Over accuracy. It doesn't have over accuracy, but still as a reference, 80%, 70%, not 90%. At least better than this, right? I know this is maybe not so reliable, but better than this. 100% is wrong. So people ask me this question: what's the difference between accuracy and accuracy? So here is from the dictionary, found out some ability, power, capacity, represent efficacy, and accuracy is agreement, conformity, correctness, that kind of keywords. They're different concepts, but efficacy is derived from this. This is the foundation. Accuracy is the foundation. Now again, if you want to assess the math accuracy, you want to see what is the accuracy for math. You have to use the math accuracy method. Nothing wrong with over accuracy in this case. Okay, you see the 100% agree, 100% accuracy. That's true. We know that's true. But if you want to use that to explain your model's prediction power, that's wrong. Cannot represent model prediction power. That's the issue. But if you only want to assess the math itself, nothing wrong with it. This is okay. It's up to your interpretation. How do you interpret the accuracy? But the accuracy itself, nothing is wrong with that. But if you want to assess the model discriminative power, you better use accuracy. So that's why you have to use the right tools for the right job. So that's my point here. Other considerations briefly. Okay, no, it's late. So simple random sampling in remote sensing supposed to be used better to generate confusion matrix. In that case, your accuracy measures, your efficacy is reliable, can represent the total population. But the thing is, very few people do that. They use stratified sampling. When you use stratified sampling, you have to convert stratified sampling error matrix table into population error matrix table. And every time in the future, I hope this is some of my advice to my students, my colleagues, my friends. Next time want to use kappa, think about the efficacy. Either you don't use them at all. If you use one, use efficacy. No kappa anymore. I want to give you briefly how to calculate the efficacy. The efficacy calculation is easy, but we develop a short. To me, I'm not a programmer. No, I'm not. I'm too old to do the programs. I used to do programming before, 30 years ago, but now only use Excel. Excel is only to use. So this is a data set, latest data set. 10 meter land use land cover data, supposed to be for entire Earth, but not yet. So you have this paper published. We got the accuracy assessment. We have this confusion table published. Once you see the confusion table, and you can, using this template, we developed this Excel template. You can copy paste that table into this template. You can calculate these numbers easily. So that's my little contribution. It works. It's not fancy, but it works. Another thing is, I don't want to go to this too much. When people are using deep learning, people are now using this to measure a lot. One is error and ROC. ROC is a traditional modeling evaluation index. Now it has been used in deep learning image analysis. The error and precision recall curve. Precision recall curve. This is supposedly more powerful. If people using this kind of curves to examine the performance of a model under different threshold decision threshold, because deep learning models don't predict hard classes automatically. You have to assign the threshold 0.5, 0.6, 0.7 to this defined class. People do this a lot. They use a gradient, okay, from 0 to 1, and get a bunch of numbers and make a curve to compare different models. this model has this curve, that model has that curve, has been used so often. The key here issue is for this one. If you look at the area, this is triangle area constant. The key is the distance from this point to this random line. The random line, the distance is the key. Greater the distance, better the model. So turn out this distance is the producer accuracy minus the false positive and proportionate to that. So we can simplify this index actually. So this one, okay, this is many people just calculate the area. If you only calculate the area, this one has a recall precision. Both have the suffers from class imbalance effect. So then error under precision recall curve cannot be so effective. Only effective if you consider this baseline. Some people do that. Some people consider the baseline. Next week, the speaker from West Virginia University, he published a very important paper, review paper. He suggests you have to use this baseline. Only you consider this baseline. This index will be effective to remove the class imbalance effect. Turn out this baseline classification same as efficacy. Efficacy is just using exactly the same thing. The proportion of the class. Proportion of the class is the baseline classification. That's the random classification. Then now they only use this baseline. I would suggest you also using this baseline to make it more effective. So that's my talk. Thank you. Here is the link. Go to the Excel file.
Open book questions.
Yeah. Any questions?
I start with one. This is a very interesting way of approaching accuracy. Remind me about some earlier discussions in hypothesis testing as well. So, in a simple statistical term, people will test y equals to a plus bx. See if a is different than 0 and b is different than 0. The hypothesis, the null hypothesis, a should be equal to 0, b equal to 0. And the discussion in the literature now is saying the fundamental hypothesis is that you should not be compared a is equal to a plus bx equal to 0. Rather, you should be compared against this to some known knowledge in the field. What is the p-value, what is the slope, what is the intercept. In your case, you're advocating, let's don't compare this to the naive background, but let's compare it to the random generated classification.
Yeah.
So I think the idea is very similar.
Similar, yeah.
My question to you is, how are you going to generate the random? Because in a lot of the situations, you might not have baseline knowledge, what the random is. But for, let's say, national land cover land use, maybe there is some, in a known situation, you'll have a background. With an unknown situation, how are you going to generate it?
Yeah, you have to know the population. The assuming key assumption is the reference data represent the population. Your reference represents population. That's the key assumption. If you don't have that assumption, you cannot get that random classification. Yeah, you can. And in other words, your class proportion cannot be true if you don't know the population. If your reference data doesn't represent the population, that's the key.
In your opinion, would this be more applicable to a large scale analysis, or would this be?
It's up to how you use your sample. That's why I said you want to do simple random sampling. This for deep learning, this is no problem because you use a lot of data, a lot of reference data. Only a small proportion 10%, 5%. That's a lot of data. So a lot of reference data. In that case, it's okay. That's more reliable to generate population, the proportions. But for traditional remote sensing, you only can sample limited number of points. That case is hard. The conversion part here, that's not perfect way to do, but that's the only way. You have other way to do. Yeah. All right.
Okay, to just continuing that question, to just create random samples many times. For example, we just create, we have a reference data from each class. So for the first time, I select randomly from each class and then evaluate my class using this random. So give me a measure. Then again, select another data randomly, but during data selection or sample selection, I consider the proportion of each class.
Okay.
In this case,
The key is for remote sensing application here, we don't know the real proportion. We use a reference map. We use the map. The map is a target we are going to assess, but we assume the map is correct. That's wrong with the stratified sampling. That's another issue. The stratified sampling based on the map. We just create it, then we want to assess it. But there's no other way. And there's no other way to do, and no other choice. In my case, in my XML class, for typical content, one class, one lab. As a student, each student randomly select 200 points for this bounded area. Don't think about any class. 200 points, one student, 200 points, we have 20 students, you can generate 4,000 points. In that case, this is true random, not class dependent. I think this is the right way to do. And if you do classification experiment, this is the cheaper. Because if you do the stratified sampling, every time you got a map, stratify, every time you got stratify, you have too many stratified samplings. Turn out it's not accurate and more effort. Maybe just in the beginning, you select enough number of points. That's like a deep learning classification. You have reference data first. Everything ready, then you run the model. That way is, I think it's cheaper, more reliable.
Any questions from online? Okay, well, for the interest of time, we are already 2 minutes over. I think it was a fascinating topic, and I'm sure there'll be more discussions afterwards. So, yeah, well, thank you again.
Thank you.